Hello everyone, welcome to our presentation, a statistical analysis to explain the different factors affecting life expectancy. In this project, we will conduct an investigation about the different elements surrounding life expectancy, such as demographic variables, income composition resources like education, healthcare, human developments, and mortality rate. Now let's move on and introduce our team. Now let's introduce our team. My name is Carlos Esteves and I'm gonna be presenting this data analytic project alongside my colleagues Renew Kartkilian and Peja Rath. Throughout this investigation, we will explore the different factors and predictors related to life expectancy, and in addition, we will build different models to understand this relationship much better. Now let's take a look at the agenda. First of all, we will give a brief introduction of the project. Next, we will show the data processing part, including how the data was collected and the source of information. Then, we will present our exploratory data analysis. In that sense, we will delve deeper into the exploration of the data, and we will answer important questions related to life expectancy. Afterwards, we will show the different parametric and non-parametric models that we have built to understand the different elements that have an influence on life expectancy. Then, we will present the results of these models. And finally, we will give our conclusion of the entire project. One of the main goals of this project is to provide statistical and practical insights to different entities about many aspects related to life expectancy in different countries. We will explore the data, employing many techniques to refine it and to gain a deeper understanding. Finally, we will build some models in order to understand the relationship between the predictors and life expectancy. For our analysis, we utilize a CSV file containing life expectancy information and a large number of features. This data set serves as a foundation for our endeavor to explain the different factors related to life expectancy. And more importantly, this data was collected from the World Health Organization and United Nations website. In this sense, in this data set, we have 193 countries. The data was collected from the year 2000 and 2015. We have 2,938 observations. In that sense, we have 20 predictors. We will conduct our analysis using these predictors, and we will determine the most important ones in terms of the relationship with life expectancy. And finally, last but not least, we have 2,563 missing values. We will show you in this analysis how we dealt with this number of missing values. Here we are presenting the list of predictors of our data set. As you can see, we have three columns. The first one is the variable name, the second one is the description, and the third one is an indicator whether the variable is categorical or not. If you want to delve deeper into the description of these predictors, you can pause the video. However, we are going to show you an example in order to better explain this data set. First of all, we have here Spain in the year 2014. This is one of the records of the data set. We can see that Spain is a developed country. This is the status of the data set. Along the same line, Spain has a life expectancy of 82.6. In terms of adult mortality, it has 58. It means that 5.8 probability of dying between 50 and 16 years old, and so on and so forth. I'm going to continue explaining the most important predictors according to our analysis, but again, you can pause the video and take a look by yourself if you want to delve deeper. BMI is one of the most relevant predictors, and it has 66. In this part, we have included a table that explains how this indicator is really calculated. We can see that Spain, in average, the average citizens in Spain, they are obese because the scale is over the chart. Another important factor or predictor is income composition resource. Income composition resource is an indicator that is expressed between 0 and 1. The higher a country's human development, the higher the indicator. Spain has a very high indicator, and this is the way in here we are showing the way the indicator is really calculated, or the different factors how the indicator is calculated. Build an accurate model aiming to understand the different factors related to life expectancy. It is very important to refine the data. As you can see in the table, we are counting with different predictors. However, some of them have a large number of missing values. We found that using just one approach for dealing with the missing observations was not the most effective way. As a result, we used different imputation strategies to address this problem. The first one, replacing missing value using the mean. This strategy is the most basic one, and we use it for some predictors that didn't have any relationship with other predictors, like population. Strategy 2, replacing missing values with the mean of all developed countries or developing countries. For example, Bolivia is a developing country that didn't have any GDP value in any of the years. So we found that a good approximation was to replace those missing values with the average of the developing countries. Strategy 3, replacing missing values using backing period. For some predictors like hepatitis, there's a relationship with other predictors like country, like the status of the country and diphtheria. So we use this imputation method to deal with this problem. Strategy 4, replacing missing values with the most recent years. For example, alcohol predictors, most of the missing values belong to the year 2015. So we replace these missing values with the year 2014. Strategy 5, in some predictors like total expenditure, only 1 year was missing. We realized about that. So we decided to replace the missing year with the average of the rest of the year. Strategy 6. In the case of income composition resource, one of the most important predictors, there is a positive linear relationship with the schooling. So we built a linear model using schooling and the status of the country to predict the missing values. And finally, strategy 7. Strategy 7 is a combination of strategy 5 and strategy 2. Handling of extreme values. Another important factor that we realized is that there were many extreme values for some predictors in some countries. For example, Canada. In terms of Canada, we have an observation of 9% vaccination in terms of polio. We know that Canada is a developed country, so this is very strange, this is very weird. I mean, this is very low. The polio vaccination is very low for a developed country. So we decided to look it up and validate this information from the World Health Organization website. And we realized right away that there was some kind of mistake, maybe collecting the sample, because the correct data is 96. So we implemented some algorithms in order to make the correction of this problem. We used the IQR and we used the percentage of deviation. Now we are going to show you the results of the detection of the extreme values. For polio vaccination, this is the data set before running and performing this the detection of these extreme values, and this is the end result. Much better. We also identified the same thing happening for diphtheria, and we applied the same algorithm, and this is the end result. In this EDA analysis, we will respond to different questions. For example, what are the factors that really affect life expectancy. Can a country having low life expectancy increase this figure by investing more in healthcare, human development, and education? Does adult mortality really affect life expectancy? Is the consumption of alcohol really related to life expectancy? What is the impact of immunization coverage on life expectancy in terms of polio and diphtheria? Now we are going to continue with the EDA analysis. This is the distribution of life expectancy. We can notice that the distribution is slightly skewed to the left. However, there is not evidence of long tail or significant extreme values. It seems that we might not need a log transformation in further analysis with respect to life expectancy. Now let's continue with the EDA analysis. In the first graphic, we appreciate the behavior of life expectancy in different countries. The big bubble represents country over 79 years of life expectancy. Middle bubbles represents countries between 60 and 79, and small bubbles, these little ones, represents country with lower than 60 years of life expectancy. We can see right away that countries like Canada and US, they belong to this category. There's a relationship with the developed countries and life expectancy, and we know that. Okay, in the second plot, we are showing the analysis of income composition resource for different countries. The big bubble means that it means countries that invest over 80% in income composition resource, middle between 40 and 60, and small lower than 40. We can see again that countries like Canada, US, and Australia, they all have a big investment in terms of HDI or income composition resource. Now, this is the relationship that we were talking about. Notice how life expectancy grows as the income composition resource indicator increases. This is the end result of our analysis in terms of finding the most important and potential elements in terms of life expectancy. We have also included this correlation matrix, and we have lighted the correlation coefficient of these important predictors. Now we will show you some of the analysis we conducted to determine these potential predictors. We can see here a box plot for developed countries and developing countries, and we can notice right away that developed countries have a higher life expectancy. Another important relationship that we have mentioned before is HDI or income composition resource and life expectancy. We can notice here the strong relationship between both variables. And the same thing for polio, GDP per capita, and other predictors. And finally, we have performed log transformation for some predictors, like percentage of expenditure by GDP per capita and GDP per capita.
Let's take a closer look at the relationship between life expectancy and the percentage of income from the most important resource, income resource percent. When we group the data by the development status of the country, developing and developed, we create a graph to visualize this relationship. Now what the interesting here is that when we compare the two groups, developing and developed country, the pattern of life expectancy versus income resource percent appear quite similar. In other words, it seems that the impact of the income resource percent on life expectancy does not significantly differ between these two groups. This similarity suggests that there are no strong interaction effect between status country and income resource. This means that the relationship between the income resource percent and life expectancy remain relatively consistent across different country development status. Therefore, we can confidently conclude that we do not need to include the interaction term between status country and income resource in our module. This simplifies our module while still allowing us to capture the essential factor influencing life expectancy. For our initial module approach, we adopt a similar linear regression method, leveraging the entire of our predictor variable with the exception of country. Our decision to utilize this comprehensive set of predictor was grounded in the visual analysis of the data, revealing that it is exhibit normality and a consistent standard deviation. indicative of a normally distributed dataset. As a measure of module performance, we assess the root mean square error or MSE. The results were as follows. For the training dataset, the OMSE was calculated to be 3.32. This indicates that the module predicted performance within the training dataset. For the validating dataset, the module produced an OMSE of 3.14. This provides a clear indication of how well our module generalized to new and unseen data, confirming its stability and reliability. To enhance the predictive performance of our module, we explore the feature selection method known as GLMNet. This technique allows us to shift through a multitude of predictor variables to pinpoint the most influential one. As part of the process, we evaluate various combinations of alpha and lambda value to arriving at the optimal module. The crux of our selection criteria was to minimize prediction error with the ultimate goal of achieving the smallest OMSE. After careful analysis, the GLMNet method leads us to the optimal module configuration characterized by alpha equal to 0.1 and lambda equal to 0.0163214. This value represents the ideal combination that effectively minimizes the prediction error in our module. It's worth noting that our module achieved an OMSE of 3.35 on the training dataset and an OMSE of 3.14 on the validating dataset. This means that, on average, our module predictions are off by approximately 3.35 units and 3.14 units from the actual value, respectively. To shed some light on the significance of alpha and lambda, alpha equal to 0.1 controls the balance between lasso and ridge regularization. A lower alpha emphasizes a lasso regularization, which encourages sparsity by driving some coefficient to 0, effectively perform feature selection. Lambda equal to 0.0163214 determine the strength of regularization. Smaller lambda value implies stronger regularization, which help prevent overfitting by constraining the magnitude of coefficient. To refining our predictive module, we turn to lasso method as an alternative approach. Lasso is known for its feature selection capability and regularization, which can enhance model performance. Why we chose to employ the lasso method? Lasso excels in two critical aspects. Firstly, it performs feature selection, allowing us to identify the most influential predictor while ignoring less relative one. Secondly, it employs regularization, which helps prevent overfitting, ensuring that our module generalizes well to new and unseen data. To assess the effectiveness of the lasso module, we use the root mean square error or MSE as our performance metric. This allows us to gauge how well our module prediction align with the actual value. After lasso module modeling process, we identify a set of variables that prove to be the most influential for predicting life expectancy. This including year, adult mortality, per expenditure, malice, polio, total expenditure, criteria, Q8, teen per year 5 and 9, and income resource. These variables are carefully selected based on their impact on our response variable, life expectancy. In terms of the model performance, our lasso module exhibits an OMSE of 3.37 on the training dataset and a 3.31 on the validating dataset. This means that on average, our module prediction are off by approximately 3.37 units and 3.31 units from the actual value, respectively. While the simple linear regression indeed exhibit a lower OMSE when comparing to both GLMNet and lasso module, our decision to adopt the GLMNet module was deliberate and driven by the strategic consideration. GLMNet, distinguished by its unique ability to perform feature selection while incorporating regularization, stood out as the preferred choice for several key reasons. In particular, GLMNet feature selection enabled the identification of the most influential predictor within our dataset. This feature is invaluable in enhancing the interpretability and generalizability of our model, allowing us to focus on the most impactful variable. Despite the fact that the GLMNet module displays an OMSE on par with the simple linear regression, we deem this slight trade-off as an acceptable compromise. The benefit of feature selection, which contribute to the module clarity and robustness, outweigh the marginal increase in OMSE. In summary, we embrace the GLMNet module for its advanced feature selection capability, recognizing that it is represent a strategic choice that enhance our module utility and understanding, even when the RMSE match that of the simple linear regression. Let's dive into the intriguing interpretation of some of the coefficients in our module, shedding light on how different factors influence life expectancy. First, we have the per expenditure, which represents the percentage of total expenditure on health. The coefficient here is approximately 0.415. This means that for every 1 unit increase in health care expenditure, we observe an increase of about 0.415 year in life expectancy. In other words, investing more in healthcare tends to lead to a higher life expectancy. Next, income com resource reflect the income composition of resource. The coefficient for this variable is quite substantial at approximately 30.81. A 1 unit increase in income com resource translates to an impressive rise of about 30.81 year in life expectancy. This signifies that countries with a greater income composition from various resources tend to enjoy significantly higher life expectancy. Lastly, the coefficient of schooling is approximately negative 0.276. Surprisingly, this implies that as the level of schooling increases, we tend to see a slight decrease of about 0.276 year in life expectancy. However, it's important to remember that this relationship may not be as straightforward as it seems, and other factors may be influencing this outcome. In conclusion, our module highlights how investing in healthcare and income composition can positively impact life expectancy. Additionally, it suggests a complex relationship between schooling and life expectancy, indicating that multiple factors contribute to this complex relationship. Our statistical analysis also revealed a coefficient for adult mortality of approximately negative 0.013. What this signifies is that for every 1 unit increase in adult mortality, we observe a slight decrease of approximately 0.013 year in life expectancy while holding all other variables constant. This finding highlights the importance of addressing and reducing adult mortality as a critical factor in improving overall life expectancy. While the effect may not be dramatic, it highlights the significance of public health intervention and policy aimed to mitigating the impact of adult mortality on a population life expectancy. In conclusion, our analysis suggests that adult mortality indeed play a role in shaping life expectancy, emphasizing the importance of effort to reduce mortality rate among adults for the well-being of the population.
So moving on to the non-parametric models. The first approach we took was the k-nearest neighbors approach. This model determined that k equals 9 was the most optimal, and it generated a training RMSE of 9.01 and a validation RMSE of 8.79. The model was trained with 10 crossfolds repeated just once. Next, we tried another approach at the k nearest neighbors. The model determined k equals 30 to be the most optimal, and the model was trained with 10 crossfolds repeated once, but the tune grid was expanded. It generated a training RMSE of 8.81 and a validation RMSE of 8.59. This has lower training and validation RMSE when compared to the first approach of k nearest neighbors, but this is not the most optimal. As you can see on the graph, starting at k equals 9, and as you continue to increase your k values, the RMSE also decreases. But this is not the most optimal because a higher k value can imply overfitting of the training model, which then makes it less reproducible for future models. The next approach we took was the regression tree model. The regression tree model yielded an RMSE of 3.3, and 95% of the residuals fall below the orange line. As you can see on the graph, this seems to look like a normal distribution with some slight skewness to the right. It shows that most squared residuals fall below the orange line, indicating that the model's predictions are relatively close to the actual values. The next approach that we took was the random forest method. The random forest method yielded an RMSE of 0.98, and 95% of the residuals fall below the orange line. This seems to look like a narrow normal distribution looking at the graph, and random forests are known for their robustness and ability to handle complex relationships. The fact that it performed well is a positive sign, but we should be cautious about overfitting. Next up, here we're comparing our models, just the non-parametric models, against the simple linear regression model from earlier. As you can see, the random forest is the most optimal because it has the lowest RMSE of all the different non-parametric models that we tried. Lower RMSE is a good sign as it indicates better predictive performance. And this goes on to suggest that on average, the random forest model's predictions are closer to the actual values than those of the other models. A low RMSE of 0.98 suggests that the random forest model is performing well in terms of predictive accuracy, which is what we want when we want to apply it to the future. And here we're comparing our models. So here, initially for the parametric models, we tried simple linear regression, GLMNet, and Lasso, and found GLMNet to be our optimal parametric model with the lower validation RMSE with some complexity. We then went on to try KNN, K nearest neighbors, regression tree, and random forest for our non-parametric models, and found the random forest to be the most accurate with the lowest RMSE. When we compare the models' RMSE for both parametric and non-parametric, it seems that the regression tree model, which has a validation RMSE of 3.3, would be more in line and closer to the validation RMSE generated by the GLM model, which was having a validation RMSE of 3.14. But the lowest RMSE is generated through the random forest model, thus making the random forest the most optimal model for our purpose. In conclusion, our presentation covered a comprehensive analysis of the dataset for predicting life expectancy. We began by doing EDA, exploratory data analysis, to clean the data and identify important correlations and patterns, and transformed some predictors as needed. We then went on to analyze a few linear regression models and a few non-parametric models. Through our analysis, we found that a lot of predictor variables associated strongly with life expectancy, including income composition of resources, schooling, BMI, body mass index, polio, diphtheria, HIV/AIDS, status of the country, whether it was developing or developed, adult mortality, percentage expenditure, alcohol, and GDP. In Objective 1, we focused on building a linear regression model that emphasized interpretability and provided detailed information regarding summary statistics on the exploratory data analysis and model building process. In Objective 2, we compared multiple models, including a non-parametric random forest. We used the validation RMSE to measure the fit of the models for comparison. After evaluating carefully, the non-parametric random forest model emerged as the best performing model with a low validation RMSE and highest predictive potential. Overall, our analysis emphasized the importance of conducting exploratory data analysis, selecting appropriate models, and incorporating complexity to enhance predictive capabilities. The random forest stood out as a promising model which can be utilized for future predictions. This concludes our presentation. Thank you for your time. If you have any questions, please feel free to reach out to any of us. Our emails are on the screen. Thank you.